Imagine spending like over $650,000 a year just to keep the gears turning in your industrial operation.
And just, writing it off as an unavoidable cost of doing business.
Exactly. I mean, we are not talking about some major capital expenditure here or like a complete facility overhaul.
Right. No, just routine maintenance.
Yeah, routine maintenance that's just bleeding a balance sheet dry. And it's all because of something completely invisible to the naked eye.
It's crazy when you really think about it.
It really is. So welcome to today's deep dive. Our mission today is to take a stack of case studies along with some technical specs and figure out how microscopic particles of dirt and ambient moisture manage to quietly dismantle these massive industrial operations.
Which they do constantly.
Right. And more importantly, for you listening, we're going to explore how a surprisingly elegant intervention in like fluid dynamics and contamination control can just entirely flip that script.
Yeah, the materials we're looking at today are great. We've got a case study from a major construction materials manufacturer, another one from a Pacific Northwest pulp and paper plant, and the technical specification data for a line of products known as the Air Sentry X-Series Desiccant breathers.
Yeah, and it is just a perfect cross-section of sources for understanding how, the smallest environmental variables can create these catastrophic operational shockwaves.
Absolutely, because we often think of heavy industry as being this robust, impervious thing, right?
Yeah, big metal machines.
Exactly. But machinery is actually incredibly sensitive to its environment. Like when you look at that construction materials case study, you really start to see the sheer scale of the vulnerability.
Oh, for sure.
I mean, we're talking about a footprint of 15 different manufacturing facilities.
Which is huge.
Yeah, housing a combined total of 500 heavy-duty gearboxes.
And just to put that in perspective for you, these gearboxes, they aren't small components. They are the primary drive systems keeping the production lines moving.
Right there, the heart of the plant.
And the numbers in this operational report are just severe. The company was spending in excess of $650,000 annually simply to maintain and repair those 500 gearboxes.
Just staggering.
Okay, let's unpack this, because to fight off equipment failure, their strategy was essentially brute force.
Yeah, it was.
They were just executing complete oil changes on every single gearbox every 6 months.
Which, I mean, that frequency of oil replacement is a massive red flag.
Is it?
Oh, yeah. It points to a fundamental misunderstanding of what is actually happening inside the machinery.
How so?
Well, when oil degrades that quickly, it is rarely the oil itself failing. It's contamination.
Ah, gotcha.
Like in a construction materials plant, the ambient air is heavily laden with silica dust and, particulate matter.
Right, it's super dusty.
Exactly. And when that dust enters a gearbox, it doesn't just settle at the bottom nicely.
I'm guessing not.
No, it mixes with the lubricating oil to create what is essentially a highly abrasive lapping compound.
Oh, wow. So it's actively grinding down the gear teeth every single time the machine turns.
Precisely. And it gets so much worse when you factor in moisture.
Because the air has humidity too.
Right. When water vapor enters the gearbox and condenses into the oil, it starts this chemical reaction called hydrolysis.
Hydrolysis, okay.
Yeah, which basically breaks down the base oil molecules and destroys all the beneficial additives in the oil.
Oh, man.
And furthermore, under the extreme pressure of the gear teeth meshing together, those water molecules actually shear apart.
Wait, they physically break apart?
Yep. And this releases free hydrogen atoms that penetrate the microscopic structure of the steel gears, which causes hydrogen embrittlement.
Which means?
The steel literally becomes brittle and microcracks.
That perfectly explains the staggering financial math laid out in this case study.
Yeah.
I mean, to mitigate all that grinding and cracking, those 15 facilities were combining to use over 10,000 gallons of lubricants every single year.
Which is just a crazy volume of oil.
Right. At an average cost of $14 per gallon, that's $140,000 burned on fluid alone.
Just on the fluid.
Yeah, but the fluid is just the tip of the iceberg here. The human and operational costs are where the real bleeding occurs. The report outlines like a minimum of 1,000 man-hours annually just for the physical repair and maintenance of the gearboxes.
Yeah.
So at $40 per man-hour, you add another $40,000 to the tab.
And then, you arrive at the most critical metric in manufacturing, which is downtime.
Oh, yeah.
Because when maintenance requires a production line to stop, the financial impact just compounds exponentially. The case study estimates the production line downtime exceeded 1,000 hours across the whole enterprise.
Valued at $500 per hour in lost produced goods.
Well, that's bad.
That is $500,000 of lost revenue capacity, purely because they had to stop to change dirty oil and fix degraded gears.
Yeah, so add the downtime, the oil, and the labor, and you easily clear that $650,000 threshold.
Right. This is like throwing out a perfectly good car engine every 6 months just because you drove down a dusty road.
Right.
Rather than just, installing a good air filter.
That is a great analogy. What's fascinating here is that this is a textbook example of a reactive maintenance loop.
Treating the symptoms.
Exactly. They were treating the symptoms, the degraded oil and the failing gears, because they assumed the contamination was just an unavoidable fact of life in a dusty plant.
Which I'm sure a lot of people think.
Oh, that assumption is incredibly common. The paradigm shift didn't occur until their corporate maintenance manager began exploring contamination control as what they called the first line of defense.
First line of defense.
Right. The logic is totally straightforward. If you can intercept the abrasive particulate and the moisture before they ever ingress into the fluid reservoirs, the oil retains its chemical integrity.
And the gears don't experience that induced wear.
Exactly. But executing that across 15 diverse facilities, that requires precise engineering data.
Which brings us to the intervention. So they brought in Air Sentry, who didn't just ship them a pallet of filters.
No, they did their homework.
Yeah, they executed a contamination control plant survey, or CCPS.
Which is so crucial. An operational survey of that magnitude is critical because industrial machinery is not one size fits all.
Right.
The engineers had to map the specific fluid dynamics of every single gearbox. They needed to document the operating environment, the total fluid volume, the viscosity of the oil.
Basically everything about how it runs.
Yeah, and especially the specific airflow requirements of each machine during operation. You really cannot prescribe a contamination solution without first understanding the volumetric breathing rate of the equipment.
Okay, wait, I want to pause right there and push back on this concept of the machine breathing.
Okay, sure.
Because it seems to me like there is an obvious, super low-tech solution staring us right in the face.
Let's hear it.
If airborne dust and humidity getting inside the gearbox is the root cause of $500,000 in damage, why do they not simply weld the gearbox shut? Like put a heavy-duty hermetic seal on the housing, close it off entirely from the factory air, and just trap the clean oil inside forever? Why does a sealed metal box need to breathe at all?
It is a totally logical question, but it collides directly with the laws of thermodynamics.
Okay.
Specifically, the ideal gas law. See, when a heavy-duty gearbox is static, the air and oil inside are at the ambient temperature of the facility.
Right, room temp.
But the moment you power it on, the mechanical friction of those massive gears generates immense heat.
Oh, of course.
And as the temperature inside the metal casing rises, the air and the oil expand significantly in volume.
So the internal pressure spikes.
Sharply. If you were to hermetically seal that gearbox, that expanding volume has literally nowhere to go.
It would just pop.
It would build until it violently blew out the rubber shaft seals, resulting in a catastrophic loss of lubricating oil.
Yikes. Okay, bad idea.
Yeah. Therefore, the gearbox must be vented. It has to push air out as it heats up.
Okay, I follow the expansion part. But if it's pushing air out, how is the contamination getting in?
Because the cycle reverses.
Oh.
When the production run ends or, the ambient temperature drops overnight, the gearbox cools down. The internal fluid and air volumes contract.
So it creates a vacuum.
Exactly. It creates a vacuum inside the housing. So to equalize the pressure, the gearbox actively sucks in air from the surrounding factory floor.
Wow.
And if you just have an open vent pipe, the machine inhales all that silica dust and the ambient humidity straight into the clean oil.
So it's literally inhaling the environment. You can't seal it, so you have to filter the breath.
Exactly. So based on the data from that contamination control plant survey, the recommendation was to install Air Sentry X-100 desiccant breathers on the gearboxes. The breather acts as this highly specialized environmental gateway. It permits the necessary airflow for the thermal expansion and contraction, but it processes that air before it ever reaches the oil.
And the results detailed in the source are just phenomenal. They utilized third-party testing to analyze the oil after the breathers were installed, and the data showed the water and particle contamination had actually dropped below ISO cleanliness standards.
Which is huge. Achieving specific ISO cleanliness codes is the absolute gold standard here.
Oh, really?
Yeah, the International Organization for Standardization uses this multi-part code to quantify the exact number of microscopic particles per milliliter of fluid at like the 4 micron, 6 micron, and 14 micron levels.
Very precise.
Super precise. And dropping an ISO code by just a few digits can mathematically double or even triple the fatigue life of the internal bearings.
And we definitely see that mathematical reality play out in their savings. Because the oil was actually staying chemically stable and clean, they reduced their scheduled oil changes from twice a year down to only once a year.
Amazing.
Yeah, that instantly cut the $140,000 fluid budget in half. But the cascading operational savings are what truly transformed the business. Gearbox failures dropped by 50%.
Wow.
Maintenance expenses dropped by 50%. They recovered 500 man-hours of previously lost downtime. So in the very first year of implementation, this company saved $340,000.
It is a perfect validation of that first line of defense philosophy. By investing just a fraction of their budget into intercepting the root cause at the atmospheric level, they entirely eliminated the mechanical and chemical symptoms that were draining their capital.
Right, and that proactive approach works beautifully in a dusty construction manufacturing environment. But it raises a new question for us.
Okay.
What happens when the primary threat is not solid particulate, but the very atmosphere of your facility? Our second case study pivots from dust to a notoriously hostile environment, a pulp and paper processing plant in the Pacific Northwest.
Oh, yeah. That is an incredibly challenging operational theater. The geographic region is already defined by high ambient humidity and constant precipitation, right?
Yeah, it rains all the time.
And then you introduce the manufacturing process itself. Pulp and paper processing inherently relies on massive volumes of water, steam, and heat. The ambient relative humidity inside the facility is constantly pushing the upper limits.
And this customer wasn't starting from zero. They already understood the chemistry we discussed earlier. They knew water destroyed their hydraulic oil, so they were already utilizing standard desiccant breathers on their reservoirs and gearboxes.
Right. They were trying.
But the environment was so aggressive that it was just defeating their proactive measures.
Yeah, they were facing a severe capacity issue. A standard open system desiccant breather works, but in an environment with near total humidity, the desiccant material inside the breather reaches complete saturation incredibly fast.
Yeah, the case study notes they were forced to replace the entire breather unit every 3 months.
Ouch.
4 times a year per machine. They had to halt the equipment, unscrew the saturated breather, throwing away the heavy plastic housing, the threaded mounts, the internal filters, and install a completely new unit.
That is just so wasteful.
It is. The maintenance labor and the replacement part costs were eroding any efficiency they were gaining by keeping the water out of the oil.
And this really introduces the concept of total cost of ownership, or TCO.
Right, TCO.
Because in industrial engineering, the initial purchase price of a component is often the least important variable. TCO encompasses the purchase price, the frequency of replacement dictated by the environment, the labor cost to execute that replacement, and of course, the financial penalty of the downtime required to do it safely.
All of it.
Yeah. So they needed a solution that would dramatically lower the TCO without compromising the fluid cleanliness.
Well, here's where it gets really interesting. Their solution was an upgrade to the Air Sentry X-Series. But the defining feature for this specific application wasn't just the quality of the filtration, it was the physical architecture of the unit.
Right.
The X-Series utilizes a permanent housing with a replaceable active cartridge. They shifted to a model where the expensive structural components remain on the machine and only the exhausted desiccant is swapped out. It's the classic razor and blade model, but used for industrial savings. Instead of buying a whole new expensive razor every 3 months, you're just swapping in a cheap new blade every 6 months.
If we connect this to the bigger picture, it is a highly efficient operational model. Instead of discarding the engineered plastics and all that mounting hardware every 90 days, the maintenance technician simply opens the housing, removes the spent silica-gel cartridge, drops in a fresh one, and seals it back up.
Easy.
Yeah, the time required for the intervention drops to a fraction of a complete unit swap.
So let's look at how that impacts the total cost of ownership, because the source breaks down the math over a 3-year timeline for just a single breather point.
Let's hear it.
With their legacy disposable breathers, changing them every 3 months meant spending $396 in year 1. Over 3 years, the total cost for just one machine's breather was $1,188.
Okay.
When they deployed the X-Series, the initial capital outlay for the permanent housing and the first cartridge was $166.
And here's where the operational shift really happens. Because of the engineering inside the X-Series, which we'll explore shortly, the lifespan of the cartridge actually doubled.
Wait, really?
Yeah, they didn't have to touch it at month 3. It lasted all the way until month 6.
And that 6-month replacement cartridge was only $47.
Wow.
Yeah. So the year 1 total cost was $230, an immediate 27% reduction in cost. In year 2, they only needed 2 of those $47 replacement cartridges, making the year 2 cost just $94.
That's a huge drop.
Over the full 3 years, the total cost of ownership for the X-Series plummeted to $448.
Compared to the $11,188 they were spending previously, that is a 65% reduction in maintenance costs.
Amazing.
And as the case study points out, that financial figure strictly measures the parts cost. It doesn't even attempt to quantify the value of having their maintenance interventions from 4 times a year down to 2.
Oh, true.
Yeah, the operational uptime gained by not stopping the machinery is likely worth magnitudes more than the savings on the plastic housings.
Okay, so the replaceable cartridge clearly drives down the total cost of ownership. But I am hung up on one crucial detail in this case study.
What's that?
How did the X-Series actually double the lifespan of the Desiccant from 3 months to 6 months in the exact same humid Pacific Northwest paper mill?
Good question.
I mean, to understand that, we need to dive into the final source document, which is the technical specification chart for the X-Series line.
Yeah, the engineering specifications reveal a highly deliberate approach to fluid dynamics and atmospheric control here. Let's start with the active medium. The entire X-Series lineup utilizes 100% silica-gel to capture moisture.
Right, those little packets you find in shoe boxes.
Exactly. But it's vital to understand how this material operates. Silica-gel does not absorb water like a sponge soaking up liquid into its volume. It operates through adsorption with a D.
Adsorption. So what is the actual mechanical difference between absorbing and adsorbing?
Absorption is a volumetric process where one substance permeates another.
Okay.
Adsorption is a surface phenomenon. Silica gel is engineered with millions of microscopic intercepting pores. This gives a single bead of silica an astronomically high internal surface area. So as humid air passes over the bead, the water vapor molecules physically adhere to the surface area within those microscopic pores through, like, molecular attraction.
Oh, I see.
Yeah, it traps the moisture as a vapor before it can ever condense into liquid water inside the machine.
Got it. And looking at the spec chart, this product line scales aggressively based on the volumetric demands of the machinery. Like the baseline X50 model holds 0.6 pounds of silica gel with a max moisture adsorption capacity of 3.68 fluid ounces.
Right.
The X100, which was utilized by the construction company, holds 0.8 pounds and absorbs 4.91 fluid ounces. But the heavy-duty models, the X502 and X522, these are massive pieces of hardware.
They really are.
They stand 10 inches tall, hold 2.7 pounds of silica gel, and boast a maximum absorption capacity of 16.56 fluid ounces.
Which, by the way, capturing over 16 fluid ounces of water vapor from the air is a tremendous amount of moisture.
It's like a whole bottle of water.
Exactly.
Huh.
But the more impressive metric on those larger models is the airflow rating. They are rated for a maximum airflow of 20 cubic feet per minute, or CFM.
That sounds like a lot.
Moving 20 CFM of air is a substantial aerodynamic event. The engineering challenge is moving that volume of air through a densely packed bed of 2.7 pounds of silica beads without creating an unacceptable flow restriction.
Because if the restriction is too high, the machine creates too much vacuum trying to breathe, right?
Correct. Excessive pressure drop across the breather would starve the hydraulic reservoir of air and potentially cause pump cavitation.
Which is bad.
Very bad. So the geometry of the X-Series housing is specifically designed to distribute that 20 CFM airflow evenly across the desiccant bed. That maximizes the contact time with the silica for moisture absorption while minimizing the aerodynamic drag.
Okay, that perfectly explains how it handles the volume, but it still does not explain the longevity in the paper mill. I mean, plenty of breathers use silica gel. What stops the 2.7 pounds of silica in the X-Series from just sucking up the humidity from the factory air in a matter of weeks?
Well, that brings us to the defining innovation on the spec chart, the dual check valve technology.
Okay. The chart lists a specific metric for this.
Yeah.
Check valve PSI in-out. For the smaller models, it's set at 0.3 PSI. For the larger high-volume models like the X522, it is set at 0.1 PSI.
Right.
This sounds like an environmental airlock. So what exactly is a zero point 0.1 psi check valve doing? Is it essentially acting like a bouncer at a nightclub, refusing to open the door to the outside humidity until the pressure differential inside the gearbox explicitly demands it?
That is the exact mechanism, yes. A standard desiccant breather lacks these check valves. It's an open system.
Meaning air just flows freely.
Right. Because the airflow is unrestricted, the silica gel is in constant contact with the ambient environment. The silica gel does not know if the machine is running or turned off. Its molecular attraction simply pulls moisture from whatever air it touches.
So in a highly humid environment like a paper mill, an open breather acts as an unintended dehumidifier for the room.
Yes.
It just sits there day and night, saturating its own silica bed with factory humidity, even when the production line is completely shut down for the weekend.
It depletes its operational lifespan just by existing in the room.
Wow.
And the check valve technology completely intercepts this flaw. By utilizing mechanical check valves set to 0.1 psi, the internal silica cartridge remains hermetically sealed from the outside environment. The ambient factory humidity simply bounces off the exterior of the housing.
So the airlock remains closed until the machine actually needs to take a breath.
Precisely. The valves only unseat when the physics of the machine demand it. When the gearbox heats up and the internal pressure expands past 4.1 psi, the outward check valve opens, allowing the exhaust air to vent safely.
Okay, and then the reverse.
Conversely, when the machine cools down and creates a 0.1 psi vacuum, the intake valve opens. The ambient air is pulled through the silica bed, the moisture is absorbed, and dry air enters the reservoir. And the moment the internal pressure equalizes, the spring-loaded valves snap shut, resealing the silica.
That isolates the desiccant, so it is only ever doing the work of drying the specific volume of air that is actively entering the machine. It's brilliant. That is exactly why the Pacific Northwest plant doubled their cartridge life. Their old open system breathers were just sponging up the paper mill's ambient humidity 24/7. The X-Series was effectively turned off, unless the machine was actively inhaling.
It really is a masterclass in aligning an engineering solution with the realities of fluid dynamics and environmental exposure. When you combine the check valve isolation preserving the desiccant life with the replaceable cartridge system driving down the structural costs, you achieve that 65% reduction in total cost of ownership.
Man, when you look at the totality of these sources, the through line is incredibly clear. We have traced how microscopic particulate and water vapor create cascading failures, hydrolysis, hydrogen embrittlement, and abrasive wear that can act as a staggering $650,000 drain on an operation.
And we've seen how shifting to a proactive first line of defense, utilizing check valve isolation and smart fluid dynamics, can neutralize that threat entirely. The overarching lesson here is the profound difference between treating systemic symptoms and addressing root causes. The industrial mechanics are specific, sure, but the principle of preventing friction at its source is universally applicable to any complex system.
That is exactly the takeaway for you to consider today. Whether you are optimizing an industrial plant floor, analyzing supply chain logistics, or even just managing a complex software stack, the core lesson applies. Addressing and isolating the invisible root causes of friction is exponentially cheaper than constantly paying for the symptoms, like broken gears and wasted oil.
It always is.
So if a simple pressure relief valve and a few pounds of porous silica can save a company hundreds of thousands of dollars just by controlling the air a machine breathes, what other invisible friction points in our own daily operational systems are we currently accepting as an unavoidable cost of doing business? What is your hidden monster just waiting for a simple first line of defense?